Well, thank you very much for that introduction. I view this as being a. See, how do I move it forward? Just click the right hand. If I can use this, okay. So I view this as being a kind of an experiment. In the title, it's the Tyndall lecture on environmental change, not just climate. Climate is part of the environment, and even though I'm a climatologist, I decided to go outside my comfort zone a little bit here and just try some stuff out, and we'll see how it works. And also, just to acknowledge that this, when you talk about the environment as a whole, that's a huge subject, you know. And there's a fair amount of overlap in this with a very nice talk that was given by Jeffrey Sachs on Monday over the lunch hour, especially with all the acceleration issues that he was pointing out. So there's been two other talks in this series. The first was by Ray Pierre-Humbert on successful predictions, and the second one was last year by Bill Redmond on early agriculture and its effect on climate. This is a picture of John Tyndall. He lived from 1820 to 1893, died at 73. This picture this etching was created when he was about 52 years old. And so what was he known for? Well, first of all, his investigations in physics, as Rong just pointed out, magnetism, diamagnetism, the flow of infrared radiation and its absorption and emission by gases. He was a mountaineer, a very outstanding mountaineer, had a lot of first ascents, and the mountains were a personal and a scientific passion with him. He also believed very strongly in science for the citizen and delivered a lot of lectures on popular science and the issue of science literacy. He's a fellow of the Royal Society at 1852, so he's 32 years old. A year later, he became a professor of physics at the Royal Institution and served in that capacity for 35 years. He was the successor to a really outstanding scientist by the name of Michael Faraday, one of the brightest guys in the history of physics, I think. And he is credited with 16 books and 145 papers. There's a very interesting article written on the web by Michael Reedy, who is a professor at Montana State University. He called it the two deaths of John Tyndall. First of all, his physical death in 1893. He married a much younger woman. He was 55 and she was 30. This bears on a point in a second. And he wasn't feeling very well, and he asked for some drugs for insomnia, and she gave him accidentally an overdose of chloral hydrate, and he died of that. The second death was what you would call reputational. She suffered a lot of guilt over his death and had a lot of concerns about his legacy, because he was a pretty well-known scientist at the time. So she began to collect thousands of pieces of correspondence. I think it turned out to be 8,000 or 9,000 in the end. And she did this for 40 years, but it never got assembled into a compendium of his life, like has often happened for other outstanding scientists. So he never achieved the lasting status of other illustrious Victorian scientists. There are now major efforts to address this. One of these is the Tyndall Correspondence project. You can just Google it if you want to see it. But they've got a lot of his stuff online. And he liked to tinker around like a lot of guys do. With stuff, and this is just a sample of the sort of the experimental apparatus that he was fond of working with. All kinds of gizmos and little valves and so forth you can play with. I don't expect you to read all of this, and a lot of these slides are just sort of for my own benefit, just as much as yours. But I show this to illustrate his breadth of interests, which span things like glaciers, heat, radiation, sound, biography of Faraday, natural history, light, electrical phenomena, diamagnetism, and magnetocrystallic action, whatever that is, and a variety of other things here. And I think he was affected by something. Richard Feynman has a really nice turn of a phrase for this, which is he called the pleasure of finding things out. I think a lot of you in the audience experience this, and I do too, and I think it's kind of fitting for his life. I have another way of putting it, and it's something I've been interested in everything my whole life since I was like 2 weeks old. And somewhere in high school, I came across this, this nice aphorism from a guy by the name of G.K. Chesterton. There are no uninteresting things, only uninterested people. And that's his yearbook picture, not mine. So to get onto this, the issue of the environmental issues, we have in front of us this host of seemingly overwhelming environmental issues. So just to go through some of them: population growth, energy generation, fossil fuel depletion, greenhouse emissions, climate change, extinction of species, anoxic ocean waters, habitat destruction, invasive species, ocean acidification, sea level rise, overfishing, mining, groundwater, pesticides, habitat fragmentation, endocrine disruptors, eutrophication, overfertilization, water conflicts, overgrazing, sprawl, nuclear waste. I can just go through the list here, and if you want to hear more, there's some more, and it just goes on and on and on. And you know, it just seems to lead to this: well, it's going to send you down to the pharmacy to get more Tylenol, or maybe next door to the saloon as your only solution to even grappling with these things. The other feature that I wanted to point out, and this is Jeffrey Sachs talked about this quite a bit too, is if you look at the metrics that describe the histories of these things, many of them, they're going along kind of flat, and then they have this, you know, look at the population curve here. That's the last 12,000 years of human population. It goes along and then bang, you know, it's just like an explosion went off. Carbon emissions, I have one here of open source pubs, which is kind of recent. But there's, I think Sachs showed must have been 20 of these types of curves. They're all look like a pure exponential, which is down in the right-hand corner there. The outstanding thing about a pure exponential, f of x equals e to the x, is all the derivatives are e to the x2, and this is a function that's going somewhere. I don't know if we want to go along with it, but that's the way it works. And so this issue of increasing rates of change is really one of the things I wanted to address here. And it's not simply a matter of the magnitudes of the issues, but really a lot of it is a rate issue. This stuff is happening so fast. Some of it has happened before in the past, but it's happened much more slowly. And undoubtedly, there are thresholds, unknown thresholds being crossed in many cases that we don't even know about. Furthermore, we've got a whole bunch of these curves that are all going along and sailing up. They're all interacting with each other. Some of them are derivatives of other curves are related to them. They're interacting in nonlinear ways and simultaneously. And you folks are lucky enough to be in a really unique period in all of Earth's storied history, which goes back 4.54 billion years now. There's been a lot of major global crises before, but they didn't have 7.3 billion people on the Earth at the time. So this issue of accelerating frameworks is something I want to spend a little bit of time on. So when you leave here and you go out to get a cup of coffee or a beer or something after this talk, and or go across the street, to navigate our way through life, we we take a snapshot of where is everybody, and then half a second later another snapshot, and we do a little projection, a linear projection, of well, where are they going to be in another half a second, because you don't want to bump into them. You know, so, and we just keep doing this. We constantly adjust, relinearize on multiple time scales. We make a bunch of short-term predictions and update these as the situation demands. And I think of this as like a Taylor expansion, which I have down here on the bottom. F of x evaluated at a point A, there's a constant term, there's a first derivative term and a second derivative term, and so forth. And I sort of look at a lot of things in life in this kind of manner. And we're describing position here, like x, y, z, your position in space. But you could think of these things in more generalized coordinates, describing the state of some system. And they have constant terms and first derivative and second derivatives and so forth. We make use of these linear projections all the time. But I think we have a much, much more difficult time projecting into the future when acceleration is present. First of all, it takes extra time. You have to have one more data point to get an acceleration. It takes extra time to get that. It requires extra processing power. It takes us away from the attention we want for other things. There's larger error bars associated with it. And And I just don't think we do as well with accelerations, nearly as well as we do with this sort of a linear projections. At times these can be extremely important, quite obviously. Other times we can assume them way to be zero. And it's even worse if the acceleration itself is changing. You know, like when you drive a stick shift away from a stoplight and you pause momentarily in the acceleration to shift gears, that's the third derivative. It's called the jerk in physics. Sometimes it might be the jerk behind the wheel too. So what equips us to deal with change in our lives? I read a really interesting book, and I've got several books I'll talk about here. This one's The Social Conquest of Earth by Edward O. Wilson. The first thing is our genetic inheritance. And life had been present on the Earth in an unbroken chain, as far as we can tell, for about 3.5 billion years. This is a slow and inefficient, but ultimately very effective process. It's harsh. You know, it's got some not so pleasant things associated with it, but it's worked. And it's based entirely on our past experience. Evolution does not look forward, it only looks backward. It's going from someplace, not to someplace. The second thing is cultural systems. These are systems of belief and our behavior patterns and so forth. This builds on our genetic history and our inheritance. It's been a long time in gestation, quite a few generations of borning, but it's fast and it's adaptable. It has unlimited growth potential. In the end, it's pretty clear that cultural, the ability to change through culture is going to be much faster. It's going to win out over genetics. It's just a question of time. Both factors, according to Wilson, seem to guide our behavior and thinking. We have selfish impulses. We have altruistic impulses. The selfish ones seem to operate a little bit more in the short term, the altruistic on the long term. There's a lot of issues that come into the climate change, like you just heard in the previous talk. They have about equal influence, although there might be a slight imbalance toward altruism. But for now, we're stuck with this mixture that we have inherited from the past in the way that we deal with the problems that are in front of us. And I might use an analogy. The sun hasn't been out too much here lately, but if you go out on the pavement out here and the sun shines down and the asphalt is absorbing the solar radiation, it heats up the molecules. They start jiggling around a little more. They touch the air molecules next to them. They heat them. They pass on heat through a process of diffusion to the atmosphere, and then more and more of those get together, and pretty soon the equation of state starts to apply, and little parcels of air start to rise up. Others come down and replace them. And we have a process that starts up called convection. And convection is a much, much more efficient way of transferring energy in the atmosphere than diffusion is. And I would make the claim that genetics operates like diffusion and culture operates like convection. And Rong just mentioned the PACE program that we have, which is where we take climate scientists and put them in a decision-making environment to learn how that works and so forth. And I call that people convection. Moving people back and forth from one place to another is a pretty efficient way of moving knowledge from one place to another, rather than having them read the literature and all that sort of stuff. So this reminded me of something I learned back in grad school in a course I took on general systems theory. It's called the axiom of experience, wherein the future will be like the past because in the past the future was like the past. And this is a sort of a heuristic that many of us take into account, and it's a really useful thing. There's no question about it, but maybe it's getting in our way when we're operating in accelerating frameworks. So I liken this to, you know, I live in the Great Basin over in Reno. So when you're driving across one of these playas and you see a mountain range come up and you're driving along and there's the windshield in front of you, but we're sort of driving along and we're getting ready to climb this steep mountain, like all these curves I've just been pointing out here. But we're looking in the rearview mirror as we're doing it, because this is our history. This is what we came equipped with. You know, this is the way we're put together. And maybe not projecting as much into the future as we could or should be. This whole issue of change is really nothing new, whether it's slow or traumatic. A couple of really nice books that really reminded me of this a lot. They both centered around the day that Columbus put his foot in the sand in the West Indies. Prior to 1491 and then after 1493, there's been a lot of changes taking place. But even so, the scope, the diversity, the magnitudes, the rates, and the number of contemporary changes really seem to dwarf the past changes. This is expressed in an Inuit expression, the Earth is faster now. There's a book, Faster, by The Acceleration of Just About Everything by James Glick about 10 years ago or so. So I want to flip now to another passion of John Tyndall, which is the mountains. He wrote these couple of books here, Hours of Exercise in the Alps. That sounds fun. But he was trying to trace out the paths of the glaciers, for example, and on the right-hand side, he was following the dust deposition and how it got distorted because it's moving faster in the middle of the glacier than on the sides and so forth. So he tried to combine these two things. Another reason why we're so interested in mountains, they're just very attractive to those of us who live in the western states. I just threw in a bunch of gratuitous pictures here just to maybe wake you up a little bit. So this is the High Sierra Nevada. This is on a flight looking out of Southwest Airlines over Mexico, coming into San Diego on final last summer. The Mount Morrison kind of reminds me of Teddy Roosevelt's description of the Tetons, mountains the way they were meant to be. Or the sort of forbidding aspects of mountains. If you ever read Frankenstein by Mary Shelley, there's some elements of that in there. This is the towers just south of Mount Whitney. And this is Mount Timpanogos, just near where we had our mountain climate meeting a couple of months ago. So I've got a picture of Reno here, also taken out of Southwest Airlines window. So I take a lot of pictures out of airplane windows. And there are three things I'd like to point out here, if I can get the cursor to work. Yeah, okay. So there is the airport right there, which is sort of in the middle of town. The precip gauge is in between the two main runways. They get 7.5 inches of precip, about the same as Phoenix, Arizona. On the outskirts of town here, it's about 12 inches. You go up to the road that goes over to Lake Tahoe, 55 inches, and at the top of Mount Rose, about 70. This distance is about 12 miles. There's a 10-fold change in precipitation in about 12 miles. We got a city here that has 300,000 or 400,000 people living in it. These people are not living on 7.5 inches of precipitation. These people are living on all that white area, all the water coming from that white area up above. This is Reno's situation. This is almost every city in the western United States functions like this. They depend on water supplies that are elsewhere that fell at a different time of year. And all around the world, too. This is, I don't know the exact numbers, but it's probably about half the population of the world is dependent on mountains for its sustenance in some form, especially with water. So this is not an unimportant thing. Two other points I'd like to make here is everything you see in that picture, all this diversity and so forth, fits inside of one standard grid box on a global climate model. And at a given level, we have one temperature, one humidity, one wind speed, one wind direction, one of each to describe this whole thing, because we've got to fit 41,000 of these on a sphere, which is the number of square degrees in a sphere. So there's always this lumping that takes place. The third thing I wanted to mention is the city of Reno has a population of about 240,000 people. And that's about the size of the area you can see in this photo here. Today, a new city of Reno was added to the world in population. It's about 240,000 people a day. Tomorrow, another Reno. The day after tomorrow, another Reno. New Renos are plopping down, in effect, spread over the earth every single day. All of those people need water, they need food, they need clothing, they need various kinds of resources, they need love, attention, and so forth. Sadly, not all of them are going to get all of those things, and some of them are going to get none of those things. And I can't think of anything, I don't like to be a scaremonger and so forth, but I can't think of anything more frightening that's happening in the world than this. And the world is not getting any bigger. It's not getting any more capacious and so forth. I think this is a really good way to visualize that whole problem. So a group of us got together and formed a thing called the Surmount in 2002, the Consortium for Integrated Climate Research in Western Mountains. We've hosted 6 mountain climate workshops, the first in 2004. They're always in mountain settings. They're modeled after the Pacific Climate Workshops, PACCLIME, and I've been to every one of those since 1984. This is science in a social setting. They've sponsored AGU sessions since 2004. There were some this year too. Dinner every year. The Mapping New Terrain report, which is still current. It was done in 2006. Repeat measurements of the tops of mountains around the world to the Gloria Project and the tree line network, the upper tree line. Efforts to improve high elevation monitoring, which is far more difficult than it is at low elevations. And Connie Millar, who is sitting right down here in the second row here in the blue, has been the ringleader of this group since its inception. And she's also the editor of our Mountain Views newsletter. She does an outstanding job on that. And we met this year, just a couple of months ago, near the Uinta Mountains, the most unusual mountain range to me in the United States, East-West Mountain Range. It has a very peculiar shape to it. We spent a lot of time in the White Mountains, which are practically almost due east of here. And White Mountain Summit, it culminates in that summit there at 14,245 feet. And if you look at it, it's 10,000 feet from the valley floor to the top of the mountains. It's the deepest trench in North America. And if you take a closer look at it with a telephoto lens, you might be able to pick out here the summit hut, which is made out of stone. And you can see a couple of white dots here. These are our weather instruments. And they are reporting live every 10 minutes. It's the highest live weather transmission in North America. Just last week, they had a gust to 139. The week of Thanksgiving, a gust to 148. This is a harsh environment. We've had winds up to close to 180 miles an hour there. And these anemometers are capable of reporting even higher winds than that. They're very, very good anemometers. So we can take the short record that we have and compare it with the reanalysis. It correlates after you detrend it and deseasonalize it and so forth. It correlates at about 0.99. We can estimate the temperature from the reanalysis of the top of the mountain very, very well. So we've been able to project back to the beginning of the reanalysis what the temperature should have done on an annual basis, which is the top curve. You can see it's been warming up, and especially since about in the year, the mid-90s or so, it's warmed up a fair amount. And the bottom curve is just the summer, when things start to grow and so forth, when the temperatures get high enough. And since about the year 2000, we've had a whole spate of really warm summers, and you can bet your money that the biology is going to respond to something like this. And we have one more thing. It's called the North American Freezing Level Tracker. It also uses the reanalysis. And the freezing level is a very important quantity in the western United States. And this is a history of the freezing level, due east of here over Sequoia, Kings Canyon, and Yosemite for the 12 months that end in each October. And you can see the last year there, it's been rising. So it's gone up 150 meters or so over the past 20 years. This year, it's 350 meters above average, or about 1,000 feet above average, and it's way beyond any other year. And I know if you extended this graph 50 or 60 years previous, it's going to beat all those years too. We have other evidence of that. So there's a monument, a stone monument to John Tyndall in Switzerland. There's a picture of it. But the United States has a stone monument too. It's called a mountain. It's Mount Tyndall. And if you look in the photo here, this is Highway 395, and there's the Owens River. Mount Whitney, the highest point in the continental U.S., is right here. Straight north of it is Mount Williamson, and right next to it is Mount Tyndall. And I have a photo here of two of my favorite things, mountains. And this is my favorite photographer, Galen Rowell, doing a selfie in 1983 on top of Mount Tyndall. And he's one of the best photographers there's been in the landscape business. He was killed in an unfortunate plane crash in August 11th, 2002, along with his wife, Barbara. And a bunch of his friends got together and put together a book, which is published by the Sierra Club. It's called Galen Rowell, A Perspective. It's a very, very nice book. I'd highly recommend it in both of its text and its photos. So the last thing I want to spend the rest of my time on here was the science communication and public engagement, and a bunch of points that just sort of relate to that. Most of his books were written for popular audiences. He delivered hundreds of public lectures. He got kind of a reputation as being a little preachy sometimes. This is from Vanity Fair, 1872. But he felt that science and the knowledge that it creates are essential to improvement of the human conditions. There's strong belief in the necessity of communicating with the public, and is especially interested in reaching the younger minds. He wasn't afraid of controversy. He was a staunch supporter of his friend Charles Darwin even when many contemporary scientists, some of them of quite note, were subdued or unsupportive or even antagonistic. Tried to infuse a sense of excitement and wonder and a lifelong sense of curiosity, which is something we should all be doing with the younger generation and with ourselves. We should never let go of this. Another issue that is worth bringing up in communicating with people is the role of observations. Yeah, we do need better predictions and projections. There's steady progress on this, but I don't see any quantum leaps coming along. We have multiple nonlinear interacting systems. It's an extremely difficult prediction problem. The prediction systems in atmospheric science, as Nate Silver, the author of the 538 blog, wrote a book called The Signal and the Noise. He holds atmospheric science up as a really good model for other disciplines to follow, and I really believe him on that. It's the ensemble method in particular, has wide application to other sciences. But I think we really have to rely a lot on observations because they are to talk to people, and it's used as a starting point in talking about climate, because they're perceived as real. I mean, they really did happen, and forecasts are more like speculation. And I've come to think that an ounce of observation is worth a pound of forecast. Mostly. There's some exceptions to that. Another book, I did a lot of reading for this talk. A very nice one by David Deutsch called The Beginning of Infinity. And one of his central assertions in this book, that human progress over the last several centuries is the consequence of better explanations of how the world works. To me, this was a really kind of revelation, or a very provocative kind of thought. The title comes from the fact that knowledge starts at zero. Some of us might have negative knowledge, but it goes out to infinity. And on a line like that, no matter where you are, you're always closer to zero than you are to infinity. So that's why you call it the beginning. And he also makes the claim, and I do agree with this, that ultimately there is almost nothing that the human mind, these 3 little pounds of matter here, are capable of, is incapable of understanding. And it's just such a tremendous thing, it's hard to even find words for it. But there's really no intrinsic limit to what we can know and understand, given enough time. Another point that he makes is that in considering and planning for the future, we routinely discount the production and value of new knowledge that's going to come into being kind of from nowhere between now and when our problem that we're trying to solve gets dealt with. And we just sort of, the axiom of experience I mentioned a minute ago tells us that, well, this happens a lot. Stuff that, who thought of cell phones, the World Wide Web, all this, like in 1975. How many of you predicted the World Wide Web? Okay? And Shakespeare said it really nice. There are more things in heaven and earth, Horatio, that are dreamt of in your philosophy. And we shouldn't forget this. Another thing is the importance of networking. Stephen Johnson, a very bright guy, he considers ideas as systems, and he did it in his book, Where Good Ideas Come From, did an analysis of the past 6 centuries, and showed that we have this conception that great discoveries come from the Wright brothers, or Edison, or Henry Ford sitting in their garage, or Hewlett and Packard in their garage, or Steve Jobs and Wozniak inventing something in their garage. This sort of garage idea. It's got a lot of traction. His point is that the conference room has now replaced the garage. It's not like the garage has gone away, but I was trying to think, well, what's the equivalent here? It's probably the poster sessions, at AGU. So, is more knowledge needed? Well, yeah, absolutely, no question of this. But is that enough? No. We have to use knowledge properly. Knowledge by itself of how the world works does not itself solve problems. It's just one of the ingredients. We're hearing a lot about this issue of the co-production of knowledge. A nice painting here etching by Maurice Escher, on the co-production of knowledge. The user, the consumer of knowledge, and the provider of knowledge working with each other so that when knowledge is produced, it is delivered and usable to the consumer of the information. Often there's a big gap there. There's sufficient knowledge, but it's not expressed right. It's not put in the right form that a user can use it, and so forth. So the idea is to try to foster more of these two groups working together. We can still produce knowledge the other way, which is just through curiosity-driven research, and we shouldn't downplay that either, but this is getting a lot more attention now. We also have a very complex ecology of groups of folks, and I've been involved with almost all of these. The state climatologists have been around for about 70 years. The regional climatologists in the middle there. That program has been here for 30 years with NOAA. The RESA program, Regional Integrated Sciences and Assessments, for about 20 years. And we've got about 4 different groups that have been around for about the last 5 years or so. The Climate Science Centers, Regional Climate Service Directors, Landscape Conservation Cooperatives, and most recently the USDA regional hubs. And what is coming out of a lot of these groups is the increasing and much needed role of social science. Understanding, you know, these environmental problems, they involve humans. So how do we make decisions? How do we handle uncertainty? What biases are we subject to that we don't even realize? How do we work? Really important questions. And when it comes to communication, how and what do we communicate about such matters? First of all, to ourselves. There's a big communication issue just among our peers. And then with the public, you know, who's footing the bill for this and who wants to know what it's all saying to them. I like the way Nolan Deskin here, a friend of mine for a long time from Colorado. I'm not a social scientist, but I am a sociable scientist. And I think all of you in the physical sciences could be thinking about this. Well, how could I be a little bit more sociable or approachable in explaining what I do? There's another book, and I think a lot of you have probably read this, by Daniel Kahneman, Nobel Prize winner, and it's got a ton of really great examples of the hidden biases that work in our thought processes. I just pulled out one here. We pay more attention to the content of messages than to information about their reliability, and as a result end up with a view of the world around us that is simpler and more coherent than the data justify. And this has been a finding in psychology for a long time, that most all human beings are overconfident in what they believe. And there have been a lot of articles about why we are overconfident. So the big puzzle to me has been, why has this issue of environmental change not obtained more public traction? There's an interesting book that just came out by Stephen Gardner, professor of philosophy up at UW in Seattle. He makes a statement in there that the global environmental tragedy is most centrally an ethical failure. The dominant discourse that we hear is scientific and economic. The deepest challenge is ethical. And this kind of got me to thinking about this issue. Often we see as metaphors things like the prisoner's dilemma, the tragedy of the commons that come out of gaming theory. And he makes the point that the intergenerational equity aspect is poorly represented in the current discourse. It's almost not discussed at all, as if it's, you know, what obligation does our generation have of handing over an earth 1 or 2 generations hence, who are in the prisoner's dilemma and the tragedy of the commons? All the players are there together. Well, in this case, they haven't even been born yet. So how do we address that? How do we take that into account? There's just no discussion of this, hardly. So we're back to this. Here's our list of environmental issues. Well, there's another big issue, and there's a nice chapter in David Deutsch's book called Optimism. These seem so daunting, and they're usually negative. I sat here at an AGU meeting a few years ago where we discussed the IPCC report, and there was about 15 different talks on the different chapters. And at the end of it all, I was sitting next to Rick Rose, and I looked at it and it says, I feel like I've just been at a funeral. Just a bunch of eulogies, you know? It says like nothing positive that was coming out of this. And it says, well, how is the public going to react to this? So how do we get a sense of realism and optimism without excessive pessimism? Just start with the point that whoever solved the problem by going into it with a negative attitude that you can't solve it, there's going to be no single solution. We need multi-pronged solutions. This is not like the moon program where Kennedy said, let's put a man on the moon and return him safely to the earth. It's not like that. This is a much more difficult problem. It's a very hard problem. There's another statement that Kennedy made. We choose to do this because it is, not because it is easy, but because it is hard. And to me, this is what I like about this problem. It's a hard problem. I like hard problems. And this is one of the hardest ones I can think of. Not all forces and exponentials are negative, by the way. We have competing exponentials that are good things that are going up very rapidly too. The World Wide Web, our ability to technological communication, and all kinds of communications mechanisms. We're seeing more growth of interdisciplinary science, more interested in science in STEM type science, technology, engineering, and mathematics. We really need to work with the public institutions to reduce the stovepiping and the silos that are taking place. And another way of looking at this is these problems grew bit by bit. They grow tailpipe by tailpipe, or little bit by little bit. So maybe part of our way out of them is also a bit by bit solution. In general, I have ambivalence about scientists advocating too strongly for their own cause because they come to be viewed as just another interest group. Have to be kind of careful about that. But I think one thing that we all should be advocating quite vigorously is improving our overall knowledge base. This is a common good. This leads to the better explanations that Deutsch was talking about. And we also have a tendency to emphasize on the right-hand side there the price of education and understanding, which is a visible, money is leaving my pocket, it's going to your pocket, somebody else's place. We concentrate on the price, but we don't focus so much on the cost of ignorance, which is real and substantial. Every one of us is suffering from ignorance. And I can think of things in my own case where some medical issues could really stand, if we knew more, it could be helped out by them, but we just don't know yet. So we should just be very vigorous in keeping this in the public eye. And finally, we just can't offer endless doom and gloom assessments, the whole end is near thing. It just turns people off, they stop listening to you, and if they won't listen to you, you're not very far along. So Deutsch also brings up this very interesting kind of analogy here, or this way of looking at things, and I envision it like Charlton Heston coming down the mountain, except this time he's carrying just one stone tablet instead of two. And on one side it says, problems are inevitable, and you turn it around, it says, problems are soluble. And this is sort of a positive way of looking at our way of dealing with problems. So just a little personal note here. We all think of the world in sort of academic terms in many cases, a lot of you and me too. But I had occasion on the 28th of February this year and the 1st of March to find out that I had colon cancer. And so I looked at the doctor for a few minutes and he says, okay, what are we going to do? So it sort of turned around my way of thinking. I sat down in the hospital, wrote down a list of some of the stuff I'd like to do. And one of those things is stuff like this. But the issue is, we don't have infinite time. And what is hypothetically possible, I knew this was always a possibility with anybody. It's a possibility with a quarter of the people in this audience, that one day sort of a vague hypothetical thing turns into something which is absolutely real and concrete, and you got to deal with it. And I like Rudyard Kipling's way of putting it, this is all we can do. If you can fill the unforgiving minute with 60 seconds worth of distance, run. Just put in your time, get as much done as you possibly can, and make good use of your time here. The other thing are these long curves that go along and then suddenly go shooting up. Well, that little inflection point there is probably about 2 human lifetimes. In the U.S. is about 80 to 85 years, so put it together, it's 170 years. We have to figure all this stuff out pretty quickly, even in the scale of human lifetimes. Of all the millions of human lifetimes that have occurred, these 2 lifetimes really matter a lot in this case. So I have a few points in conclusion here. A bunch of my friends in, I think, in the California and Nevada Applications Project, one of these RESA projects, sort of put me up to saying, well, you've been working in climate for 32 years, have you discovered anything? So I thought, well, okay, I'll do it, I'll humor them. And then a few of them said, well, why don't you put that in your Tyndall talk? So this is an experiment. Anyway, just a few things picked up along the way. First of all, don't take yourself too seriously. Nature does not try to trick us or fool us, but she does wear an inscrutable poker face and show respect for both of those things. Be a skeptic about everything, including this list. Science does not stop in the classroom, the journal, or the conference room, or the laboratory. It follows you everywhere. There are no bounds to its area of inquiry, and ultimately everything is open to it. Know thy audience, if possible. AGU I'm pretty familiar with. I feel pretty comfortable talking to you folks. And try to communicate with audiences with them as one of them. They appreciate this if you take the trouble. It's fine to admit that you don't know things. A lot of people have trouble with this. Try to be accurate and precise in the use of language. This really takes a lifetime. Read good writers and explainers, lots of them. And all of those books I was just showing you, they have some pretty interesting stuff in them, so the substance is interesting, but also the way they explain things. Like, Edward O. Wilson's won Pulitzer Prizes for writing. So, pick good writers as examples. This just takes a lot of practice, and they don't always have to be in science. Guys like Steinbeck, Hemingway, Mark Twain, Melville, those people knew how to say stuff. We need to, if we're going to talk with people, we need to know how to talk. Another thing, I like this comment by George Bernard Shaw. Life does not cease to be funny when people die any more than it ceases to be serious when people laugh. The universe, to me, is just hilariously funny. You should embrace humor. And I would really like to see AGU sponsor a session next year on the role of humor in science. I think it'd be a lot of fun. Our role in higher education is to push the boundaries of knowledge, maintain an awareness of, and be suspicious of buying into conventional modes of thought. The second of the two, everybody is interested in the weather. So in my own discipline, everybody feels they're an expert. We have a built-in advantage in our profession, so work with that. The people love it. Choose competent people that you enjoy working with and who challenge your abilities. You will automatically be lifted up. I think in interdisciplinary science, it's really important, the whole social side, and working with people that you enjoy working with. Those teams work a lot better than others that have a lot of division and fractionation. There is hardly any such thing as over-communication. More often, less is more, as you can tell from these two slides. Work within your own personality. Everybody is different. Treat all members of the public with respect and as equals. Learn how to represent other people's viewpoints, which are opposing or alternative to your own, without judgment or commentary. This will gain you a lot of respect, including the respect of those people. In science, all we have is credibility. It's hard to gain credibility. It's easy to lose it. Don't mess that up. You get one chance. Pay due attention to your critics and then trust your own judgment. And finally, Richard Feynman always had great advice. The easiest person to fool is yourself. So just a couple more slides here. Not only journalists and writers can be good writers, but actually full-fledged scientists can be good writers who have written hundreds of articles about the science of climate and so forth. And Don Wubbles, who's sitting down here in the front row, wrote something up in your very own journal, EOS. It's a beautifully written essay about the blue marble, the pale blue dot. This is our home. We're not going to be leaving it anytime soon. We're going to have to sit here and solve our own problems. And I asked Don about this about a year ago, and he says, I just sat down, I wrote this from the heart. And he did a bang-up job, and it was great, Don, and I really commend it to you if you got a little spare time sometime over lunch. So the last sort of substantive slide I have here is on this whole issue of these complex and vexing and escalating problems. The solutions are going to require cross-bridging of some sort. Sure, we pay a lot of attention to the physical sciences, the American Geophysical Union, okay? But you notice in the program, there's probably 20 or 30, there might be more, sessions on communicating and on education. This is to AGU's credit. All the scientific societies should be doing this. My other society, AMS, is starting to concentrate on it quite a bit too, of going beyond just the pure physical sciences. This is, knowledge of the world is just not enough. We need to bring in findings from the social sciences, and the humanities offer a lot, the experiential part of being a human being. And we need to combine all of these three things, because otherwise we'll come up with solutions that are sort of not workable or practical. And we have to be thinking of, well, it's human beings who are going to have to solve these problems. And you know all the problems that human beings have just being human beings. So the last thing I'd like to do is whoops, I went one too far here. Is just acknowledge I've got a lot of friends that are here in the audience or maybe out there in virtual land someplace. And really want to thank them for showing up here and for being very supportive over the past 8 or 10 months in my own case. And I had the surprise of my life when just about an hour ago, my two brothers here, Pat and Mike, from Montana, showed up behind me. One is Pat's from Montana, and Mike is from Beaverton, Oregon. They came down here for this, and I had no idea they were coming. And they tapped me on the shoulder and says, okay. So I really do appreciate that from my heart. And to the rest of you that I don't know as well, thank you for coming too, and for hope there's some little morsel of something that came out of this that might be of some value to you. Thanks a lot.
So now we have a question session. Please make sure to ask a question to speakerphone so remote audience could hear. Thank you.
Hi, Kelly. This is not a question. It's just a gesture of thanks. Tyndall has always been a huge hero of mine and many in this room. And there's been a number of great Tyndall lectures. But I can't imagine having selected anyone better than you for this Tyndall lecture as a communicator and as an inspiration to a generation of younger scientists like me. And you've been a great inspiration to me and many in this room, and I hope your brothers are very proud of you.
Yeah. Thank you very much. I really appreciate that.
So I'm sure, like many in the room, I'm a great Richard Feynman fan, and I wanted to ask you about the pleasure of finding things out. What was the one or two things in your life that gave you the greatest pleasure about finding out?
I don't know if I can pin it down to one thing. I have my education. I was going to be an astronomer, and so my background is in physics and astrophysics. And like a lot of us, you know, it's cloudy a lot, so you end up looking at the sky rather than through the sky. There's always something to see in meteorology, so that's kind of how I picked that. But I think probably the biggest revelation was getting an understanding of quantum mechanics, and the way the world is put together is inherently probabilistic as a way of looking at the world, and it sort of changed a lot of the ways that I started to conceptualize the world and my own interactions with the world. And I came across a really great description of this, that the world and all the particles, all these hard little atoms and so forth, can all be described as relationships. That physical objects are nothing more than a very complicated set of relationships, and all there is in the whole shebang is a god-awful complicated set of interacting interrelationships. And I think if you carry around that conception, you can employ that in dealing with people and dealing with issues and so forth, and you don't get hamstrung by victories and defeats. You know, Kipling had another great line: "If you can meet with triumph and disaster and treat those two imposters just the same." I really feel that sort of describes a probabilistic way of looking at the world. That beer out there must be.
Yeah.
Yeah.
Yes.
Yeah, the bubbles are disappearing.
So now it's an honor to present you the certificate of Tyndall lectures.
Thank you very much. I very much appreciate this.